Our next speaker is David Berenstein.
Okay, so for those of you who don't know me, I was a student here in the 90s. When I came to Texas, was in one of these low points of string theory, where I had been told before coming here that string theory was dead and I should study something else. Half a year later, the second string duality revolution started. So this was just serendipity, but this is something that I remember. And then I'm going to talk about the bootstrap and the relation to Goldilocks will become apparent later. So this is when I started. So at that point, it was clear that the right thing to do was string theory. So let me tell you first what a bootstrap is. For those of you who don't know, shoes and boots have this extra tag that you can pull in that makes it easier to put your boots or your shoes on. Okay? So it's actually a technical device that actually makes it easier to put your shoes on. And then the story about what pulling yourself by your bootstraps is, it apparently comes from Baron Munchausen, where he pulled himself out of a swamp by pulling on his own hair. And then at some point, it became something about pulling yourself out of a swamp by your own feet, meaning violating the laws of physics. And it was considered very derogatory at the time when it started. And apparently it moved on to just, being a symbol of self-reliance and self-sufficiency. So the idea of bootstrap ideas is that, self-consistency in physics will be good enough. And this drawing, I had to find a nice one. So this came from the British Library source. So it's an 1800 drawing. Okay. So what's the bootstrap program? The idea of the bootstrap, broadly speaking, is that self-consistency of possible solutions to a problem is enough to solve the problem completely. And now there's a joke, is that if you talk to people, and what they say and what they do are very different things, being self-consistent is actually very difficult. Weinberg, was one of the few people who I know that was absolutely self-consistent in everything that he did. He wouldn't beat around the bush. When I started grad school, the idea of the bootstrap was, okay, there's the S-matrix properties, there's analyticity of amplitudes, there's crossing symmetry, and unitarity. So I get here to Texas, and then I start seeing the Veneziano amplitude. It's an analytic function, has analyticity of amplitudes, it has crossing symmetry. There's also this property that the poles in the S channel kind of give the T channel amplitude and some other stuff, and it has perturbative tree-level unitarity. And then this seems like a miracle. And then Weinberg was teaching this class, and he loved this amplitude. He spent about 3 weeks tearing it apart. And I remember him, making a point of calculating the residues at the poles and showing that there were polynomials in T. And I was a graduate student. I didn't know what polynomials in T meant. It's actually a very deep statement about physics, is that the residues are actually particles with a definite integer spin. and he loved this stuff. And I think he also liked the idea that this was kind of very hard to find formulas that did this. So he absolutely loved this class. And then, also in the 90s, I took quantum field theory later from him. And then he was going to Washington, and there was the SSE, and he was promoting the SSE. And then when they canceled it, he came into class. It was a bit grumpy. He said, well, now there's no excuse for anyone not to learn string theory. And the statement was, there's not going to be any data, so don't bother. And when I was later here interviewing for a job, I think I was in the car with him. And then he told me why he moved to cosmology is because there was data. And he loved data. He loved the idea of, just having data and being based on the real world. Okay, so what's the modern quantum field theory point of view of these S-matrix axioms is that things have moved. There's a huge number of solutions because we parameterize them by effective field theories or by field theories in Lagrangians and quantum field theory Lagrangians. So the idea is that, being self-consistent is not enough because there's many solutions to self-consistency theory. So we need to add a theory more. Okay, so now I'm going to talk about the bootstrap. And then for the purposes of this talk, I'm going to write you a model. And this is to illustrate the ideas of the Bootstrap so that you get an idea of how it works. So I will assume that for our theory, all we have to do is understand the probability measure that was handed to us that depends on some parameter B. And I know how to solve this in hundreds of different ways. Most of the audience will probably be happy with the idea of this is a probability distribution that I want to characterize. I've written it clearly here, but I will solve it using the Bootstrap. And then I will tell you how that actually looks like in practice. So I will say these are the moments of the distribution. So if you have the moments of the distribution, this is a way we characterize distributions. Usually when you have a Gaussian, you give the spread and that's it. And usually when you have data, you characterize it by various moments of the distribution, especially if you don't know what the underlying distribution is. So this is a way to characterize the distribution. You just compute the moments. So I will claim that we have solved the theory, we know all the moments. And this is the way I will solve it. I will input unitarity or positivity. So the idea is that if the measure is a positive measure, when you integrate a positive measure with a positive function, you'll get a positive answer. You're just using basic properties of positive numbers. And then if the function f happens to be a polynomial with arbitrary coefficients, this d mu f of x squared is a quadratic function of the coefficients that you use to build f. And because it's a quadratic function, there's a matrix underlying the problem. And then you can rip apart the coefficients. And then you get that a particular matrix built from the moments of the distribution needs to be a positive matrix. So a positive matrix, you know them. A covariance matrix, for example, is a positive matrix. A density matrix in particle physics or in quantum mechanics is a positive matrix. The moment of inertia tensor, that's a positive matrix. All of these things are positive matrices. And the idea is that we're going to characterize the measure by saying that this matrix of moments is positive. And I'm going to use that to solve the theory. So when you truncate the degree of the polynomial, you don't get an infinite matrix. You get a finite matrix of constraints that you need to satisfy. And then theorems in mathematics, meaning that this problem has been studied in mathematics, guarantee that if the matrix m n by n is positive for all n, and the moments don't grow too fast, meaning the measure decays sufficiently fast, the measure d mu exists and is unique. And there's a huge number of very famous mathematicians attached to this problem. There's Stilches, Hamburger, Hilbert at some point, and various other people who were doing functional analysis in the 1910 to 1940. But the point is that, I just told you that any positive measure will have these properties. So positivity is not enough. I need to now input the theory. So I need to use the theory somehow. So the idea is that, now that we have the theory, I'm going to talk about the extra constraints that I have by using the language of particle physicists, which is you compute the Schwinger-Dyson equations. So the Schwinger-Dyson equations in this case is that the integral of a total derivative is 0. And if you take in quantum field theory classes with modern path integral methods, the way you get a lot of word identities is you take a functional derivative, total derivative of something, set it equal to 0, and you get some constraints. And these constraints are the Schwinger-Dyson equations. So if you do this with this particular setup, you get a nice relation between the moments. So once you know the second moment, it's a probability distribution, so I normalize it to 1. But once you know the second moment, there's a recursion, and you can compute all the moments. So instead of having to give you all the moments, all I have to do is give you one moment. So solving the theory in this case means we only need to know A2. And the reason why I'm doing this is because I can clearly see that this is symmetric, and the x goes to minus x, and therefore the odd moments vanish. Okay. So now there's some observations. I don't expect you to know this, particularly, but one observation is that the matrix M of moments is now linear in the one undetermined moment. And therefore, the two problems, minimization over the one variable requiring positivity and maximization of the variable requiring positivity, these are two problems in semi-definite programming, convex optimization, that again, theorems in math, and people have studied these problems for engineering, finance, all kinds of places that are not just physics. They guarantee that these problems, if they have a solution, it is unique because you're doing convex, you're trying to find a maximum on a convex set. And on a convex set, if you have a convex function on a convex set, there's a unique maximum or a unique minimum. And the algorithm that you really have to follow is gradient descent or gradient ascent. And this is the class of problems that is solved completely and precisely by gradient descent. So they're fantastic problems because you don't have to do any annealing or any problem, or you have to worry about any of the problems that can show up in other systems. Okay, so these problems are solvable, and they're so useful that basically there's commercial solvers that you can just dump this stuff in. I know what the commercial solver is doing, so it's not a black box, but I don't need to program it. And then because these problems have unique solutions, they allow to determine rigorous mathematical bounds for feasibility. Meaning that if you show that something is ruled out, it is ruled out forever. It's not that it comes back and it's ruled out with some error bar. It is just gone. So let me show you what the results look for one parameter b equal to 1. You do 4x4 matrices. You get some big bound, 0.7, 0.5. That sounds a little bit like a cosmological Hubble tension about 30 years ago when I was a grad student. Factor of 2 was about right. And then you do things, 6x6 matrices, things are looking good. And then before you know it, it looks like it has collapsed. So when you look at these, I cannot see the size of the intervals. So I take the maximum minus the minimum. And then you see that as you increase the size of the matrix, this is just falling off a cliff exponentially fast. This is a log plot. So you see that and you say, okay, this is great. These will converge. So if I need to go to some large digit, I know how far to go. If you need 8 digits of precision, sometimes you do for certain problems in quantum field theory, but in general, this tells you that things are looking great. Okay. And then this is what I'm thinking about now is once you have something that actually works so well, why did that happen? Right? It's not good enough to say, okay, things are exponentially. This is good for, if you have an example that does that, this is great. Do all examples do it? Is this the norm? Did we get lucky? I'm thinking about this because usually you have to know what's going on to break it or to find a better algorithm. So I'm going to give you the bird's eye view of why this actually works in this case. Positive matrices are characterized by having positive eigenvalues. The system goes bad or inconsistent when the smallest eigenvalue of M becomes negative. So you can say, well, how small is the smallest eigenvalue? And I'm not going to answer it for this one. The answer is really the same, but I'm going to tell you a simpler model. The simpler model is you take a measure which is exponential to minus x dx. This is so simple that I can compute the moments. They're n factorial. So what you see is that the moments, these are big numbers. N factorial for n equal to 20 is a number that my old computer would have broken down, the one that I was working with as an undergrad. And I'm going to show you what the minimal eigenvalue of the matrices do. So you take the matrix of moments. They're growing like n factorial. You take a 25 by 25 matrix. The smallest eigenvalue is order 10 to the minus 6. Okay, it's a huge hierarchy of scales. You see, 20 factorial is a big number. Largest entry goes like to n factorial. The smallest eigenvalue is ridiculously low. And then if you're a numericist and you're not paying attention, which is what happened to us the first, second, and third times, this is bad in the sense that if you have a huge hierarchy of scales, you need to work with huge amounts of precision. And as soon as you do that, all the optimization for double float arithmetic that has been worked into your laptops goes out the window. And then if you're not paying attention, the first thing that happens is that you think that numerical noise is physics. Okay? This is what happens when you have a big hierarchy of scales in a numerical problem. So, the software needs to work with huge amounts of precision, which means that when you try to compete with things that can get ahead with double precision, LAPACK, and matrices, you're dead in the water. And then this statement that the eigenvalues go down happens pretty much without regard to which distribution we're using, because you can always compare the distribution that you want to another one that you know the properties of. And if a positive matrix is smaller than another positive matrix, the smallest eigenvalue of the small matrix is smaller than the smallest eigenvalue of the large matrix. So smallness of the eigenvalue means that if it's really, really tiny, you're almost at failure. Okay. So there's some natural extreme fine-tuning in this math problem, which is why the feasibility intervals, the error bars, go down exponentially. Okay, so this is a Goldilocks phenomenon. This I plotted for the 8-byte matrices, the minimal eigenvalue. Okay. This is A2, this is from 0.4 to 0.48. This is what the minimal eigenvalue is doing. It's -1 over here, the region where it actually works. This little island over here. If you think of this as the sea level, you think of this as a volcanic island, you're sitting at the only place where you will not drown. And on the next iteration, the island will sink, and there will be one spot where you will survive. And then that happens again and again, so you have to survive, and you have to be really lucky. And then this is what, you have to be not too hot, not too cold, you have to be just right. And this is what we usually attribute to Goldilocks. This is my version of Goldilocks for today. It's blonde, curly hair, does all the things, and they love fine-tuning problems, especially for the cosmological constant. So in any case, the idea is that this is one of those problems that accidentally we got this fantastic fine-tuning. And of course, once you get that, you say, of course, it has to work everywhere. One can imagine that this type of methodology could be competitive against Monte Carlo methods, which are known to be slow because you have to collect statistics. If you want to increase your statistics, or if you want to decrease your error bar by a factor of 2, you have to take 4 times more data. So at some point, it's a game of that. And unfortunately, and this is what's really happening in the field, is that not all Bootstrap problems work so nicely, meaning not all of them converge as fast as this example would show. And this is something to keep track of. Okay, so the Bootstrap, there's more than one thing called the Bootstrap. The broad ideas are the same, there's consistency, and then there's some type of objects that one puts into the consistency of the Bootstrap that, depending on which subclass of Bootstrap problems one is working with, have different flavors, and they're more or less mathematically complicated. But what I've been talking about is a set of numerical Bootstrap problems, which date back to some work of Krushansky and one of his students, Anderson, about loop equations and all that. It's about 2016. And then there's a huge amount of work that came out after this paper by Henry Lin on matrix models. And then I worked on some of the quantum mechanical Bootstrap that Han Harden or Kurhoff were describing. And then Kazakov and Sheng have been doing this on steroids for trying to solve lattice QCD at large N and plaquettes. We did quantum mechanics. We did all kinds of weird versions of quantum mechanics. We solved all the 1D problems that we could possibly get our hands on. And then when we published our paper, there were all these competitors, and suddenly we were racing to get our papers out. And then there were some papers that came afterwards that showed how this same idea could be used in spin systems. And if you actually look at the condensed matter physics literature, they call these problems a dual variational problem because the variational problem gives you, let's say, upper bounds on the ground state energy, and these similar things, you end up minimizing the energy as your idea. You end up getting lower bounds on the energy, so it's kind of the dual of the variational problem. And then, of course, we did some spin chains, and half of the problems worked out, and the other half didn't. And we don't know when it works and when it doesn't. Okay, so this is it. I'm gonna have some final remarks. It's mostly for students, but some of it is just me entertaining myself at the expense of my audience. The first one, what I want you to get out of this is that with this problem of the bootstrap that I showed you, you probably understood what was going on. You probably understood that the equations were not that hard, that there were some constraints, and that if you put enough constraints, you got something to converge. Most bootstrap problems are that way, and 90% of the talks are about the technicalities of which objects you put in and how well does it converge. The second statement is don't be afraid of numerics. It's another route to data and knowledge, and just teasing something apart that comes from numbers is a good way to get into interesting problems anyhow. The third one, find students who can actually program, and not just that they can, but that when you tell them to program, they won't drag their feet and say, I don't really want to put this on a computer. Half of the students I get out of that kind. Okay, and then this is the really important lesson, is that you might get lucky. Sometimes things work a lot better than they had any right to work out. And this is, luck plays a huge important role in physics. So you have to have your Goldilocks moment where you got lucky and all the work that you did was just exploited, so that when it was not too hot, not too cold, and just right, you were able to succeed. And then once it works, it's always good to understand why did it work. And there might be surprises. So you might get into all kinds of places. And I think Weinberg would have liked that. So thank you.
Great talk. Questions for David? Okay.
Have you done the comparison of the computational cost of the numerical method you have presented against the Monte Carlo method?
Not for this problem in particular. In this one, we would win. But in other problems, I have compared some similar problem that computes eigenvalues of a Hamiltonian to the state-of-the-art kind of, let's say, Mathematica spectral method problem. And the fact that they do it with double precision arithmetic on LAPACK and get good answers, and the fact that we have to go to infinite precision arithmetic engines to do the calculation costs at least a factor of 100 just in computing resources. So the only advantage is that we can say for sure that it's not here and not there when some of the error bars on some other methods are a little bit more squishy.
Any other questions? If not, yeah, Katie.
I'm just thinking we're in astrophysical cosmology with this wood, but I don't see lots of astrotypes here. I want to know where to use this.
If you have a good model of a distribution or something, then usually this is a consistency of covariance matrices being positive can rule out models that predict these things wrong. So this would be something where you can tell that some data is wrong by looking at some covariance and something not being right, that some covariances are too large. Problems in quantum computing optimization are also problems that fall into this category, which is why they're used in the examples of some of the documentation of this software sometimes. And because these are a problem of optimization, people in Wall Street love this stuff. So in finance, there's a huge number of optimization problems, and you want to make sure that things make sense. This is why I didn't know about this stuff. It teaches us.
Okay. If there are no more questions, well, let's thank David again.